Hello everyone, thank you so much for joining us today. I hope everyone's doing well and staying safe out there. My name is Victoria and I'm a Senior Business Development Coordinator at 2H Offshore. With many industry events and conferences canceled due to COVID-19, we've put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome you all to our webinar today entitled Optimizing Subsea Jumper Design for VIV. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we will go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Mahesh Chanane. Mahesh is a principal engineer with 2H Offshore in Houston and has over 12 years of experience in riser and conductor engineering. He is a licensed PE in the state of Texas, and he graduated from Texas A&M in 2007 with a master's degree in mechanical engineering. Throughout his career, he has been involved with over 100 drilling and intervention riser studies serving clients worldwide. So with that, I will pass things over to Mahesh to get us started today.
Right. Hey, Victoria, thank you for the introduction. I'm really excited, to be talking about this topic today. And, this is one of the topics that we presented in OME last year in Scotland. So, some of you who already attended the conference may have seen this content before. But, for those who couldn't attend that, I'm glad that we're able to do this webinar. And I hope that everyone will be able to find some useful information from this presentation. And I also want to welcome everyone because I know a lot of people are tuning in from a lot of different places. So a good morning, a good afternoon, or a good evening from wherever you are at this point. So this is the outline of my presentation today. I'll start off with a brief introduction on subsea jumpers. And then we'll also cover some basics and background on the phenomenon of VIV and especially the phenomenon of VIV in jumpers and how it is different than your risers or conductors and pipelines. We'll cover how VIV fatigue analysis is conducted, go through the methodology, and then we will jump into our case study where we'll demonstrate through the means of this case study how we went about optimizing the jumper configurations based on the VIV response. We also had some good learnings from this study, and one of the learning was regarding how cross-flow induced VIV is calculated, and we have something to share about that towards the end of this presentation as well. Okay, so jumpers. Jumpers are basically short-length pipe connection systems which are used to connect different elements of your subsea architecture. So you can have jumpers which are connecting your wellhead to a manifold or your pipeline to a manifold. You also have jumpers which connect hybrid risers to another subsea architecture like a manifold or a pipeline. So basically they're used for transporting fluids between these subsea architectures. But even though they are pieces of pipe, they are never designed in a straight shape or a straight line. So they are not straight pieces of pipe, and they come in different shapes that represent different alphabets. So you can see on the images over here, there are different jumpers like your M-shaped or Z-shaped or your U-shaped jumpers or your arch-type jumpers. And then you can have a combination and variation of these different types, and some of them even are supported on the seabed. And the reason the jumpers are designed like this in different shapes with bends so that we can give some compliance and some flexibility to these structures. Because during operations, your flow lines or your risers, they're going to have movement because of environmental loading or from pressure and thermal expansion and contraction. And the jumper has to be sufficiently compliant such that it can tolerate these displacement. And having such shapes helps in achieving that design objective. Traditionally, however, these jumpers were designed mainly for static loads. And by static loads, what I mean is these different movements and also to just support their own weight and the loads that go into the connectors. But over the period during operations, we've seen that the jumpers see a lot of dynamic loading, and hence there are few different design drivers that go into design of a jumper. So one key consideration while designing jumpers is obviously your strength. Your pipe and your connectors should have sufficient strength so that it can withstand the loads that you see throughout the life cycle of the jumper. But it also has to be designed to withstand the fatigue loading or the small cyclic loads that are induced on these jumpers. And there are different sources of fatigue. So you have slugging, which is basically flow of gas pockets or change in density of the fluid that flow through the jumper. And you can also have VIV, which is a vibration induced because of flow of current over the pipe. And you can also have flow induced vibration, which is because of the flow again through the pipe, but because of changes in the pressure or changes in the flow rates during your operations of the jumper. And lastly, you also have to design the jumper such that considering what are the installation and fabrication limitations. So you cannot, if you need a flexible, enough flex, you cannot have a large length or a large dimension jumper because you need to consider the limitations of the installation vessel and also the ROVs which are going to be handling these jumpers while installing. On this slide, we have shown a comparison of what are the different requirements and considerations that you need for your strength design and for your fatigue design. So on the left, what you can see is when you're designing for strength, the objective is to have sufficient compliance in the jumper such that even if there is variations at the two ends because of thermal and pressure expansion, or if you have a well jumper, if you have growth of your wellhead or subsidence of your wellhead, the jumper should be compliant enough such that it can tolerate these different movements. Also, you cannot install the jumper perfectly aligned, so there's going to be some misalignments in your connectors, in your end connections, and the jumper is going to see some displacements at the end, and it has to be able to withstand these. And generally, you can do this by the design mitigation used for your strength typically include choosing a good material grade such that the material your stresses in your connectors and your pipes are less than the design capacity or the yield capacity. You can also optimize the design by not over designing the jumper so that they are not excessively heavy, by managing the weight either by optimizing the wall thickness or putting buoyancy modules on them. You can control the weight and hence your end loads. And finally, an important tool designers have at their disposal is doing a very custom specific design. And by that, what I mean is when you're installing your subsea systems like your plets or your wellhead locations, you cannot get them exactly where you want them, and they're always installed in a circle of tolerance. And so the way the jumper design is done is you install your subsea systems, then you do your final metrology, and then you cut your pipe lengths according to the install architecture, and thus you avoid any misalignments and pre-stresses in your jumpers. On the other hand, when you're designing for fatigue, your main concern is your design frequency. You want the jumper to be sufficiently rigid such that it does not vibrate because of these different excitation sources that exist in your subsea system. There are different loading frequencies from VIV, from FIV, and other sources. And the objective is to avoid these frequency and have a design which lies outside of all the loading frequency spectrum. But obviously, you cannot have a design which you cannot always have a design which would avoid all frequencies. And in most cases, there will be certain sources which do induce vibration in your system, and then you have to find a way of mitigating these vibrations and coming up with a solution so that even though there's vibration in the system, you have a jumper which can withstand the vibrations for the entire service life of your field. And you do that by choosing a good weld quality, or if you have sour service, you can put cladding on your pipe. And if VIV is a problem, then you can suppress or mitigate VIV by putting strakes on them or putting some large buoys on your, or some large diameter buoys on your jumper pipe such that the VIV lock-in does not occur. If you see vibration in a system, you can also even install dampers and thus prevent excess amplitude of vibration in your system. So changing gears a bit, here from jumpers, we are going to now look at, sorry, excuse me. Okay, so going from jumpers now, let's look at some basics of VIV. VIV stands for vortex-induced vibration. And in this animation, what you can see is you have a flow of current which is going from left to right. And the black box or the black circle that you see is a cylinder. So what happens is when you have flow over a pipe, you get these vortex shedding because of flow separation, and these vortex shedding occurs at a periodic frequency. And hence you get periodic pressure fluctuations across the diameter of the pipe, and which causes the pipe to vibrate in a direction which is perpendicular to the flow of your current. This phenomena is called cross-flow VIV. The pipe also vibrates in a direction which is in the direction of the flow, and that phenomenon is your inline VIV. Just to illustrate these two phenomena, the first motion that you see for this cylinder is the inline VIV, which is in the same direction as the flow of your current. The second phenomena where you see the pipe vibrating perpendicular to the direction, that's your cross-flow VIV. And finally, you have a motion which is a combined of your cross-flow and inline VIV. We call this cross-flow induced inline VIV. And what this basically is when your pipe does your cross-flow vibration, it does not do it in one plane. It does a figure of 8. And because of that, it does have, even though it's vibrating in the cross-flow direction, it has a component of motion which is in the same direction of your flow. And that vibration occurs at twice the frequency. And you can see that from the Strouhal numbers. Your pure inline VIV, it occurs at a Strouhal number of around 0.33, whereas your cross-flow occurs at 0.18. These were the simplistic animations of how a simple straight pipe vibrates. But obviously, a jumper, it's not a straight piece of pipe, and it comes in these different shapes. And this animation over here shows how a jumper vibrates in its first mode of vibration. And this mode is when the jumper is vibrating out of plane. Now, basically what it's doing is the pipe is pivoting around the two connectors where it's connected. So if you imagine, if you stand with your legs a bit stretched out, and if you move back and forth a bit, simplistically imagining, that's how your out of plane vibration is. The second animation here shows your in-plane vibration mode. And again, in our analogy, if you're standing with your legs stretched out, if you move from side to side, that's, you can imagine that's how the mode of vibration for your in-plane direction is. Now, these are quite simplistic modes, but for a jumper, when you go higher modes, like your mode number 3, 4, and higher, the motion of the jumper or the vibration is not that simplistic, and the jumper has a lot of torsional and twisting modes, and you don't tend to see purely in plane or out of plane vibration modes. And that's where some of the challenges come in the VIV analysis of a jumper. So on the previous slide, we looked at what are the different modes of vibration of the jumper. The second consideration in VIV analysis of a jumper is what is the direction of your current. You can have currents from two different directions, like as the two extreme phenomena, if you can imagine. The first one is current coming from an out of plane direction, as you can see from the red figure on the top. And in this phenomena, what's happening is the entire length of the jumper is susceptible to VIV because vortex shedding can occur along any length of the pipe. On the other hand, if you have a current coming in the plane of the jumper, which is the second figure on the bottom, It's only the red lines or the vertical legs of the jumper that are susceptible to VIV, because those are the legs on which vortex shedding can occur. The blue lines, number 2 and number 4, since the current is flowing parallel to the pipe, it cannot induce VIV. So that's the main difference between the two directions. In one, you have the entire length, which is susceptible to VIV, and in the second one, you have only the vertical legs. Another thing to consider is you have two directions of current, but each of these directions can cause cross-flow VIV, inline VIV, and cross-flow induced inline VIV. So basically there are 6 sources of fatigue. You have 2 directions and each direction causing 3 types of VIV. And that's what you do in a jumper VIV analysis. You estimate your fatigue damage for all these 6 components and try to determine which is governing, and also you sum up these damage. Sometimes you have to do a conservative assumption if you don't know the directionality of your field. And if you know directionality and how the jumpers are installed with respect to the direction in field, then you can apply some probabilistic estimations to your in-plane and out-of-plane currents. Another thing to note is that when you get cross-flow induced inline VIV, that vibration occurs at twice the frequency of the cross-flow mode. So in doing this analysis, you tend to choose the mode which is close for your cross-flow induced inline VIV. You tend to choose a mode of vibration which is close to 2 times the frequency of your cross-flow mode. So on the previous slide, we saw directions. Now here you can see a comparison of the vibration amplitude for different sources of VIV. And this is a plot from DNV RPF 105. On your x-axis, you have reduced velocity, which is the inverse of your Strouhal number. And on your y-axis, you have the normalized amplitude, or amplitude of vibration normalized by the diameter of the pipe. And what you can see here is the highest amplitude you get of vibration is from your cross-flow VIV. And that amplitude is typically 1 times the diameter of the pipe. The inline VIV, on the other hand, shows the smallest amplitude of vibration, and it's around 0.15 times the diameter of your pipe. Whereas your cross-flow induced inline VIV is 40% of your diameter of the pipe, the amplitude of the vibration. And you can also see from the x-axis is that these different types of VIVs occur for different reduced velocities. So they occur for different current speeds. So inline VIV is the first one to occur. You can get inline VIV for reduced velocity anywhere from 1 to some number about 4. Whereas your cross-flow VIV starts at around reduced velocity of 3. Okay, so now we will move on into the case study that we worked on. And basically, we were looking to design 12 sets of jumpers for a service life of 25 years. We had 3 different types of jumpers. And for each type of jumper, we had 4 different variations based on how long or how tall they were. And in the subsequent slides, we are going to call them as long, short, short, long, and short, short. And these designations are based on the length of these jumpers in the X and the Y direction. Another thing to consider for us was the bottom currents in the field. Because of it being close to an escarpment, we are going to see bottom currents close to 1 knot in a 100-year event. And just based on that, and also considering the range of long-term currents, we knew that VIV was going to be a concern. And this was determined based on a screening study. Also, another thing to keep in mind is the production fluids were characterized by high H2S and CO2. And hence, because of this sour service, we needed to use a knockdown factor when we were calculating fatigue life on the inner diameter of the pipe. And by knockdown factor, what I mean is basically you calculate your fatigue life and you divide it by a factor of 10 to account for your sour service. Also, these jumpers, they were large diameter jumpers and very thick walled. As a result of that, they were quite heavy. And to manage the weight of these jumpers and the load on the end connectors, the designers had to use buoyancy modules, which were installed on the belly of these jumpers. Uh, since we had buoyancy modules, there was no place to mount strakes on this for VIV, and hence buoyancy modules with integrated strakes were used in this case. However, since since the diameter of these buoyancy modules is quite large and the length of the jumper is quite restricted, you cannot get a full pitch of helical strakes on your jumper. And because of that, the buoyancy modules did not have a good VIV suppression efficiency that you typically see on your riser strakes. So these were low efficiency strakes, and we had to take that into account while calculating the fatigue life. And another thing too, when the designers actually started out with this, the strakes were mounted only on the belly of the jumper. So you can see from this arrangement is that your vertical legs of the jumper, they're susceptible to VIV because they do not have any suppression on them. It's only the belly of the jumper. So if you have current coming from an out of plane direction perpendicular to the plane of the jumpers, you would get some suppression. But if you get currents in plane of the jumper, you wouldn't see any VIV suppression. Okay, so we did VIV fatigue analysis for all these 12 jumpers, and this slide over here shows the flow chart of how we went about it. So basically, for VIV analysis, first thing you do is build a FEA model of your jumper. You can use any tool that's any standard FEA tools available. In this case, we use ANSYS. And the purpose of the FEA is to do a modal analysis and calculate the modal properties of your jumpers, your frequencies of vibrations, curvatures, mode shapes, etc. And all that feeds into as an input into shear 7. We then use shear 7 for calculating the pure inline and the cross flow VIV fatigue damage. One thing that shear 7 cannot do is calculate the cross flow induced inline VIV. And hence for that, we had to use the DNV code RPF 105. So you feed your outputs from your inline and cross flow into RPF 105. And then you use the guidance in the code to come up with the fatigue damage from your cross flow induced inline VIV. So looking at the response we got for the initial configuration. So this is, just to reiterate, this is the initial configuration where we had modules and strakes only on the belly of the jumper. And what we found was we got quite a high fatigue damage for the long jumpers, for the 2 long jumpers when we were looking at long-term VIV. We were getting a fatigue life of in the region of 30 and 160 years, whereas the target fatigue life was 250 years for this case. So obviously we were not meeting the long-term fatigue life for these 2 jumpers. On the other hand, for the short jumpers, which were really stiff jumpers, we were getting a really good long-term fatigue life, but we were not able to meet the short-term fatigue life, which was a target of 160 days. And that's how much the 100-year current was expected to be in this field. So we had a problem on all 4 jumpers for both long-term as well as short-term VIV. I just want to stress that this slide shows 4 examples, but we had other 8 jumpers, and they were kind of a mixed bag where some of them were meeting all the targets, and there were a couple which we did not meet. So we had some meeting the design, whereas a lot of jumpers which needed some optimization. So moving into the optimization for VIV, what we did was we looked at the fatigue contributors for different jumpers, and what we saw was most of the fatigue damage was occurring from currents being in plane of the jumper. And this, in hindsight, this seemed to be the right trend because you saw the vertical legs of the jumpers did not have any suppression on them, and there was no suppression for this current directionality, and hence this response made quite a lot of sense. I think I've already said this. The main reason is that we didn't have any suppression on these vertical legs, and so the easiest solution for us would have been to recommend adding strakes or buoyancy modules on the vertical legs of the jumper and solve the problem. But that would have been far too easy, right? I mean, we engineers, we like to do things the hard and in the fun way. So we went about a process where uh, we were trying to borrow modules and strakes from jumpers that were doing really well and moving them onto jumpers which were not, which we needed some additional suppression. Actually, the main reason for doing the optimization was that the project was quite far along in the on the schedule, and having to order extra buoyancy modules or purchasing modules would have been a hit on schedule, and if not on the schedule, definitely on the cost of the project. So this optimization exercise really was to make sure to have make best use of the resources that we had and come up with an optimized design. So when we went, when we did this optimization exercise, we were borrowing strakes and modules from jumpers which were having good fatigue response. But while doing so, we were aware that we are deteriorating the fatigue performance of those jumpers when we are taking away buoyancy modules. So we had to be cognizant of that fact and check those jumpers to make sure they meet their target life as well. But we did come up with a configuration by moving these around and adding strakes on the vertical legs of these 4 jumpers to come up with a solution such that all 12 jumpers would meet their target requirements. And this is how the optimized configuration looks, where we had, especially for the long jumpers, we had buoyancy modules and strakes on both the vertical as well as the horizontal leg of the jumper. And by doing this, we went from around 30 years on the long jumper to 800 plus years. So quite a bit of improvement by putting buoyancy modules on the vertical legs of the jumper. So yeah, in summary, we met the target fatigue life on all 12 jumpers. One thing we did have to do was recommend adding regular strakes, and by regular strakes I mean is strakes which are mounted directly on the pipe instead of on the buoyancy modules for the vertical legs of the jumper. And the reason for this is, I think I've said this before, the strakes with the buoyancy modules, they have very low suppression efficiency. And in order to suppress the VIV from the 100-year current and meet the short-term fatigue life, we had to mount riser strakes which are close to 90% fatigue VIV suppression efficiency on the vertical legs of the jumper. Another one learning that I want everyone to take away from this one was the modification that we implemented for cross-flow induced inline VIV. So the analysis was done using RPF 105. However, it should be noted that this code is applicable to pipelines. And as per the code recommendation, you're supposed to use 40% of your maximum cross-flow amplitude and use that 40% applied to an inline mode and calculate your fatigue damage for your cross-flow induced inline mode. Also, the mode vibration mode that you choose is twice the frequency of your cross-flow mode. So basically, you're choosing a mode which is twice the frequency, and you're applying 40% of the amplitude. And when we did this, we saw that the fatigue lives were very low, in the order of minutes or hours in some cases. So we had to do a bit more digging and use some engineering judgment. And what we did was we applied the amplitude of vibration based on the power in region of the jumper rather than choosing a maximum amplitude from any location on the jumper. And the main reason for doing this is, when you saw the jumper modes of vibration, the vibration in plane and out of plane, they're quite different. You may not get you may not get your maximum amplitudes at similar locations. So in a cross-flow mode of vibration, the peak amplitude can occur in the belly of the jumper, whereas in your in-plane vibration, it may occur on the vertical legs of the jumper. And since in our case, it were the vertical legs of the jumper which were which were vibrating for in-plane VIV, sorry, in-plane current direction, we had to choose our amplitudes based on the vertical legs of the jumper. So that was the amplitude, that was the modification we came up with in consultation with the operator and also with the designers. And using this engineering judgment helped us achieve a good improvement in the predictions of the VIV for cross-flow induced inline. And these are the factors for the long-term VIV fatigue life, and you can see the improvement can range anywhere from 60 to 2000. Even though on this chart, on this table, you can see that it's our long-term VIV was not a problem for cross-flow induced, but it was the short-term VIV for the 100-year current for which we had to implement this modification and to meet our target fatigue life. Okay, so that brings me to the concluding remarks of this presentation. Just to summarize it, designing a rigid jumper based on your strength and design considerations is quite challenging because the designers are doing a balancing act because of the very contradicting requirements that you have to satisfy for strength and fatigue. Also, if you're designing a set of jumpers, 12, 16, or whatever the number, having a one-size-fit-all solution, just saying that mounting strakes on the belly of the jumpers or mounting n number of modules on certain length of the jumper would solve the problem for all jumpers is not always the right solution, because different jumpers, they have different frequencies, and their susceptibility to VIV depends on their frequencies. If you're using buoyancy modules with strakes, please be aware that these are not efficient as riser strakes because of the incomplete helical pitch that they have, and hence you need to ensure that you apply a lower efficiency in order to make sure that you're not under conservative in your VIV predictions. There's 6 different sources of fatigue. You have two directions of loading, and you have 3 sources of VIV. And any of these 6 sources can govern the fatigue damage for your jumpers. So your long jumpers may be susceptible to one type of VIV, whereas your short may be susceptible to a totally different VIV phenomena. Hence, you need to make sure that all these 6 contributors are evaluated correctly. Another key aspect of VIV analysis is the knockdown factors that you use, the SN curves that you use, and also the shear 7 input parameters that you use. And it helps to be aware that the different operators have different guidelines which are very specific to their requirements. And if you have the operators on board on this analysis right from the beginning, it can be quite beneficial. And lastly, DNV RPF 105, it's an excellent code for pipelines, but as I said, it's a code for pipelines. So the predictions that you get for jumper can be very conservative, especially for cross-flow induced inline VIV. Even DNV published a paper recently based on a JIP, and they're working towards a more jumper specific code. And I think that's one of the needs for the industry at this point. And I think there's work being going on in this field. So with that, it brings me to the conclusion of my presentation. I really want to thank everyone who attended this webinar, and now we have the floor open for questions.
Thank you so much, Mahesh. We've had quite a few questions come in, so I'll get started asking those. And if anyone else has any more questions, feel free to keep sending them, and we'll go through as many as we can. So the first question is, how sensitive is the inline VIV to the direction of the current? Does it have to be perfectly in place of the jumper?
Okay, actually, that's a good question. No, you don't have to be perfectly in the plane of the jumper. Suppose if you have currents coming in at certain misalignments, say 10 degrees or 15 degrees, you would still have maybe 95 or 90% of the current velocity which would be in the in-plane direction of the jumper. So it would still induce VIV. Even if you have the current coming in at a 30-degree angle, just based on the cosine of that angle, you'd have like 86% of the velocity in the same direction. So the jumpers would be susceptible to inline VIV, even though it's not in plane.
Okay, next question. How much is the knockdown factor for sour service and what is the justification?
Okay, so in this case, we used a knockdown factor of 10. There was, okay, ideally for a sour service, what the operators tend to do when they're developing new fields is you do test your materials for sour service, do your fatigue testing, and based on the test, based on the concentration of H2S and CO2, you would have different knockdown factors that would come from your tests. But in this case, we did not have test data, so we had to rely on the factor of 10, and that's what we used.
Okay, the next question is, do you consider composite pipes or flexible jumpers?
Actually, it is one of the emerging trends. I especially haven't worked on this, but I know there's some work going on in Asia Pacific region where they're using composite pipes for jumpers, for constructing these kinds of rigid jumpers. And obviously the benefit of composites, you have a lot higher structural damping, so you're able to have a good solution for VIV. And you can also have flexibles connecting, and just that they won't be in a rigid shape. You would have it curled up or in some shape lying on your seabed. But yeah, I think there's work being done in both types of jumpers.
Okay, next question. A near bottom flow is a shear flow. Do you take that into consideration?
We do not, but it's for the sake of conservatism. Because when you're designing, you have to make sure that you're designing have a robust design. In case if we ever see a design that's just not meeting consideration, we can apply refinement where we will consider a sheared flow. But in these cases, no, this was done a bit more conservatively using the full bottom current velocity that was available from the metocean.
Okay. Next question is, can you please repeat the amplitude values you mentioned in the representative vibration amplitude slide from DNV?
Yes. So the cross flow VIV, it occurs at the normalized amplitude of 1, which means your vibration is approximately 1 times the diameter of the pipe. The inline VIV, it occurs around 0.15 times the diameter of the pipe, and the cross flow induced is 40% of the diameter of the pipe.
Okay, thank you. Next question, has OrcaFlex been used as part of jumper design of fatigue analysis?
Yes, we recently have used OrcaFlex as well. So, I mean, we have done this exercise where we're benchmarking different softwares. We have used FlexCom, OrcaFlex, ANSYS, and Abacus. There is some variation in the predicted frequencies and curvatures, and that's mainly attributed to how the torsional effects are considered in these different softwares. But one of the key parameter that you need to consider while benchmarking your frequencies is your added mass. Since the jumper is sitting in water, the added mass when it vibrates, estimating the added mass is a challenge, and you have to do in instances where we have had test data, we were able to benchmark it by doing some sensitivities with the added mass.
Okay, next question is, do you have an idea about what is the typical amplitude of deflections due to the temperature variations in U-shaped rigid jumpers?
And
that was just
it's hard to it's hard to predict because it will be proportional to your temperature. I think you can estimate based on the length of the pipe, and if you have a very short jumper, you're going to get less deflections because it's quite stiff. If it's a long jumper, you would get higher. But no, I don't recall exact amplitudes of the top of my head.
Okay. Next question. Have there been any fatigue failures in jumpers offshore?
There have been actually, since a lot of fields in the Gulf of Mexico now they are maturing, and as they're aging. Recently, we have seen a couple of failures. Not everything I would say is because of vibrations. There was one failure which we are aware of, which was because of flow-induced vibration of the pipe, and there was another failure that was more because of the thermal expansion of the pipelines that they were connecting. But yeah, we are looking to. We are starting to see some failures now.
Okay, thank you. Next question. How confident are you in the accuracy of the strake performance? And then a follow-up to that, how confident are you in shear 7 to predict VIV?
Okay, so the strakes, they are, we have monitored risers for risers which were installed with strakes. So we see some good efficiency coming from strakes. As long as they're regularly cleaned and there's no marine growth on them, you get good efficiency from strakes. But shear 7 tends to err on the conservative side. Just from monitoring data, we know it's at least an order of magnitude conservative in predicting VIV for risers.
Okay, and I think that is all our questions. Yeah, I think we answered everyone's questions. So thank you so much, Mahesh, for all the information on the topic, and that's all the time we have for today. But as we mentioned earlier, if we didn't get to your question or you think of some more in the meantime, you can contact Mahesh directly using these details provided here. And thank you all to our audience for your time and participation. We hope you found this useful and will join us for more webinars in this series happening every 2 weeks during our time at home. You can check out the 2H website for more details and to sign up. And again, please look out for a recording of the webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. And thank you so much.